Thank you, Hongwen. Indeed, it just occurred to me I may hold the title of being the longest overlapping colleague with Eli, since Eli seldom stay in the same institution for more than 2 decades, and I overlap with Eli in 2 institutions, so I might hold that title. Let me know if there are other.
I think Axel sure might be a little longer.
But Axel is at the Caltech. So our paths crossed since about 2 decades ago. And I remember at that time I was at Bell Lab, Murray Hill. Like many before us, I'm contemplating moving to a university and considering several universities, UCLA being one of them. And one day, I was agonizing over these difficult choices, including staying at Bell Lab, and the dean at UCLA called me and told me, well, Eli Yovanovitch should just sign on to be with UCLA. I said, whoa, that makes the decision a whole lot easier. So here I go, and along with another colleague, Baron Gelati, we literally arrived at UCLA the same day, 1993, and has stayed on there for a dozen years, and now we are colleagues here again at Cal. So the subject I'm going to talk about is a collaborative project with Eli. Over our overlapping years, we work on many things together. This most recent one is one of the most exciting ones. So a little bit history before the collaborative project started. Back in about 5 years ago, we are interested in making miniature lasers, and following the initial demonstration of Martin Hills, who reported the first lasers totally clad in metal cavities. My student Amit Lankani has made this Nanopatch Laser, which features a very small diameter as well as a very small height, with a physical volume of only 2% of free space wavelengths cube. Back at that time, there's a lot of question being asked. Now that we can make the laser so small with a very small mole volume, can these various enhancement factor actually make laser go faster than the conventional semiconductor laser, which we all know are limited by relaxation oscillations and nonlinearity of the gain mechanisms. So we look into that and did a comprehensive dynamic models of these nanoscale enhanced lasers. And the results were sort of mixed. Generally, even as we shrink down the lasers, even though there are various enhancement of spontaneous emission, unfortunately, they also produce other damping factors that preclude them from achieving a higher frequency than conventional lasers. But the other side of the coin is, when you actually bias it below threshold, it can operate indeed faster than a laser. So this is a suggestion that an LED might eventually actually be better than a laser. So that's sort of the background in the backdrop of our discussions, and a sort of more serious discussion happened here. This is on our way back from one of the DARPA program reviews. It's a SERS review, Surface Enhanced Raman Spectroscopy. And the program manager lives in Minneapolis, and the PI meeting is in January. January, Minneapolis, is probably not a total surprise to run into situations like that. So on the final day of our review, snowstorm is approaching. Eli and I grabbed the cab. We rushed to the airport, and the flight we are on was canceled. And I was resigned to the fact that we might have to spend the night at the airport. Eli grabbed me and sprint to the next airline, I think American airline counters. And that sprint turns out to be the difference. We got on the last 2 seats of the flight onto Chicago, and where there are other flights that we can come back to San Francisco. So there I start to see Eli's determination and drive. And so we finally got onto the flight. Neither of us are members of American Airlines, so we are stuck in the middle seats together. And I was just about to relax and have a glass of wine and enjoy the flight back. Eli pulled out his stack of notes from the hotel and have a pen and say, "Okay, now let's get to work." He started to derive all these equations, all these plasmonic effects that we can explain with just combinations of inductance and capacitances. And one of the key subjects, as Professor Pendrin articulated very well, about the Raman effect, the surface-enhanced Raman effect, which is the main topic of our review meetings there. And they are sort of two different type of mechanisms that can lead to very high field enhancement. And Eli is a big fan of Marconi, as he just said, that if we can concentrate the field down to a very small areas, and certainly we're going to have a very sensitive Raman sensors, provided we do good impedance matching, because we all know a good antenna, the free space impedance is about 377 ohms, whereas the molecule is tend to have very high impedance. There's a huge impedance mismatch there. If we can manage to solve and address these problems, there are tremendous potential to this problem. Now, Raman scattering, in fact, is a form of a spontaneous emission offset by a different frequency from the vibration spectrums. So if this can enhance Raman sensing, naturally it should be able to enhance a spontaneous emission. And so if we go back to the light-emitting diodes, our good old light-emitting diodes, well, we know it's slow. The spontaneous emission lifetime, as we heard earlier, we thought it was a God-given parameter. It's 1 nanosecond, as we have been told from our graduate courses. And as a result, its slow bandwidth is limited to 100 megahertz also. It's incoherent. It's hard to focus them back down to small devices. So with Eli's view of how the radiation happens, it gives us a sort of a new viewpoint on how to explain the inefficiencies of a light-emitting diode. So the spontaneous emission is equivalent to almost like an oscillating dipole. And for typical semiconductor, that's only 0.4 nanometer dipole length. And as we all know, that to be an efficient radiator, it needs to be about roughly half wavelength. This is almost just 0.1% of efficient wavelengths for efficient length for radiation. And naturally, it's being a very inefficient radiator. So the obvious solution is by attaching an efficient antenna down to the nanoscale, contacting ideally just the radiating dipoles, and this will help the oscillating current be coupled into the antenna and then quickly radiating to the space. So this could potentially greatly enhance the rate of spontaneous emission as well as the intensity. And many of us who have worked with Eli all know Eli's good instinct. In addition, he always come up with a catchy phrase that immediately capture the essence of this new phenomena. So here it is, the faster and stronger than stimulated emission. I think this probably, if it eventually worked, will go down as probably one of his most well-known lines. And we feel that we need a new name for this enhanced spontaneous emission. Initially, we were thinking of super spontaneous emission, but that apparently has been taken for other things. So now we have this spontaneous hyperemission, or acronym of SHE. And indeed, if we do a little bit more careful analysis and just imagine that we have an oscillating dipole and the current, this oscillating dipole, will induce current in these metal antennas, and we can very quickly, using Raman theory, figure out the current induced in the antenna is actually inversely proportional to the gap spacing between the antennas. And from the current, you can calculate in equivalent circuit this resistance being the radiation resistance of the antenna, how much power is actually going to be radiated. And from the power that are radiated, we can estimate what is the lifetime of these antenna-enhanced nanoemitter structures. It turns out to be a very simple expressions. Compared with the bulk spontaneous emission lifetime, the enhancement factor is equal to the square of the ratio of the wavelengths, free space wavelengths, to the antenna gap spacing, and multiply by the quality factor of these combined systems. Now for LED, we do want to have a good antenna, so assuming that we have antenna Q on the order of 1, and the ratio of the wavelengths to gap spacing can be as much as 10 to the 6th or 10 to the 7th. So this Xi spontaneous emission can be a million times stronger than the bulk spontaneous emission. This dimensionality analysis also gives us a clue on how to design a practical devices. Here, we see that the penalty for this coupling to antenna is really inversely proportional to d square. So in order to achieve a higher spontaneous emission rate, we really need to contacting these emitters down to the nanoscale. To give you a rough order of magnitude of the practical parameters, in order to achieve 100 gigahertz bandwidth, the antenna spacing here should be less than 50 nanometer, on the order of 50 nanometer. A few other interesting facts is even though this spontaneous emission is still temporarily incoherent, but now that it's coming from a subdiffraction limited regime, the radiation is actually spatially coherent, and it is possible to focus that back down to, for example, a nanodetector. So this sort of a qualitative conceptual comparison of these nano LED and laser structures. We compare them in the DC transfer characteristics. The laser have a well-known threshold and turning on with a quantum efficiency defined by the cavity loss and the output coupling loss. The Xi LED doesn't have a threshold. It's a spontaneous emission process. The first photon recombine, the first electron hole pair recombine will be radiated. The efficiency, which many of us worry that it will be low, actually is governed by the same quantum efficiency expression. Is basically the ratio of output coupling to metal loss, and so that's why it's represented by the same slope here. If we look at the dynamic responses, we know that the laser frequency, characterized by the relaxation oscillation frequency, is proportional to the square root of how high the laser is biased. In other words, the photon number inside the cavity. So in order to achieve substantial bandwidth, we need to bias the laser at several times of the threshold current, typically at least 5 times the threshold current. In comparison, this Xi LED, the first photon emitted can be fast. And this gives a tremendous advantage in terms of the systems that the circuit does not need to provide any DC bias. Well, how do we implement such a structure? It turns out that we can almost mimic that of microwave antenna structures. We do need to provide some kind of matching circuit, since there's usually a large impedance mismatch. This is one structure that my student Michael Eggleston is pursuing. It is a dipole antenna, but around the emitters there is arch mimicking that of inductors. And we have performed the design, and more detailed simulation shows that indeed the light the light inside this semiconductor is very well coupled to the antenna with a total Q of the system of around 7, indicating it is a good radiator. And the loss is equally distributed between the radiation loss and the metal loss. And that turns out to be the most efficient point we can design such emitter. The mole volume is about 0.01 of the half material wavelength cube. So the fabrication is indeed quite challenging for such a small structure. In order to reap the benefits, we have made this nano emitter semiconductor structure made in indium gallium arsenide phosphide to be on the order of 20 nanometer in width, roughly about 30 nanometer in height. It is patterned by electron beam lithography. In order to provide a good impedance matching, we have removed the substrate and put the structure on a ground plane. So all the radiation will be aired up in phase, in free space. So this involves wafer bonding, substrate removal, 2 e-beam lithographies. This shows you the close-up of one of such structures. We do have to take care of the step coverage of a metal. In this particular case, the metal is a little bit broken, but we have other antennas where the metal is continuous. And we have performed some early measurements, preliminary measurements of these devices. So again, this is a top view of a picture. And to give you an idea how we do the testing, we do optical pumping and measure the micro photoluminescence. Because to help our fabrication alignment, we simply have a continuous strip of semiconductors, and the antenna is crossing the active strip as shown here. We did not remove the materials in between the antennas. So if you look at our probing areas, we have roughly 10% area that's strongly coupled to the antenna. And about 90% area is still just like nano-rich material itself, and that will still radiate. So here is the photoluminescence results. Here we compare the polarization of light emitted in the vertical direction, that is, they are parallel to the active strip and perpendicular to the antenna. It turns out that for native structures, light in such a nano-confined structure tends to radiate strongly in this polarization. We see literally no difference between the structure with a nano antenna and the structure without antenna. However, if we turn our polarizer 90 degrees and collect light in the direction of antenna radiation, that is parallel to the antenna, horizontal in this case, and here we see quite a bit of difference. There's very little light coming out from the control samples, but we see much enhanced light coming out in the structures with the antenna. And in addition to just the luminescence peak, we see this slight peak shift corresponding to the antenna resonance wavelengths. And we can also compare with structures with misaligned antenna. If the antenna is misaligned, we don't see much effect. And when antennas start to couple to the emitters, we see stronger enhancement. So this is very encouraging, and if we do the accounting calculation, we'll show that the total enhancement, if we account for both polarizations, we see about 17 times total enhancement. But if we were to remove the materials in between the antennas and ideally just have a quantum dot underneath the antennas, in the polarization direction, we have observed indeed greater than 100 times enhancement. So this is very encouraging towards the path of a faster and stronger than stimulated emission goal that we have started with. So this is where we are, and where do we go from there? And looking at all the great presentations this morning, and other great talks that will follow, and looking at Eli's amazing accomplishments. It's not hard to find that each of Eli's accomplishments has turned into a successful company. So we are all waiting here for the 5th company to be started. And to conclude, it has been truly a privilege and honor to be a colleague of Eli Yovanovitch for nearly 20 years. Thank you.
Questions? Comment?
I would say not all of them have. Some of them have not even been successful papers. Never mind successful companies. But do you normally take pictures of snowy airplanes in Minneapolis? Where did that come from?
So to be honest, in full disclosure, that is not the airplane we are on. That is airplane I search on the web, pull down as close as I can. And as you can imagine, there are abundant of pictures of snowy Minneapolis airport pictures.
So you saw that indeed with the antenna you had more light coming out of the array. So is it faster than the structure width of the antenna? Did you do any speed measurements of your structure?
Speed measurement, yes, that's sort of a holy grail that we all like to do. The light coming out, the absolute intensity is actually quite weak due to the very, very small active volume now. So we have not been able to do dynamic measurements yet, but that's certainly one of the to-do list.
Any more questions? If not, let's thank all the speakers.